Welcome to Mastering Solutions. For this question, let's write down what we're given. They give us a diffraction grating with 600 lines per millimeter, so let's figure out what D is. And that's always going to be the width over the slits or lines, same thing. And they tell us it's per millimeter, so 1 millimeter is 1 times 10 to the negative 3 meters, and divided by 600 lines or 600 slits. And I'm going to leave it like this because we can just plug that into the calculator without having to worry about rounding or anything like that. And then we need to figure out what's the distance between the two fringes. So the angle that we're going to use, actually before I get into that, let's write down the equations that we'll be using for this. So the first one that we'll be using is sine of theta is equal to m lambda over d. The second one that we'll be using is y is equal to L tangent of theta. So we need this one so that we can isolate theta. And that's theta is equal to the inverse sine of m lambda over d. And then that we can plug in down to here. So when we rewrite that, we have y is equal to L tangent of inverse sine m lambda over d. All right, so now this is the equation that we'll be using for this question. So let's go ahead and plug everything in. Oh, we can figure out some more stuff. Let's see, the viewing screen is 2 meters behind the grating, so L is 2 meters. And the wavelength, so lambda, is given as 500 nanometers, and that's, of course, 10 to the negative 9 for nano. And I believe that's everything that we need. So now let's plug that in up here. So y is equal to L, which we said was 2 meters, times the tangent of theta, which we said was inverse sine. And m, we're talking about m is equal to 1. Lambda is 500 times 10 to the negative 9 meters. And that's divided by d, which we said is 1 times 10 to the negative 3 meters divided by 600 slits. All right, so what does that give us here? We have 2 tangent of the inverse sine, and then 1 times 500 times 10 to the negative 9, and then that'll all be divided by 1 times 10 to the negative 3, divided by 600, and that gives us 0.63. So we have 0.63 and it's y, so that is meters. Now there's probably a lot of students, maybe some have gotten that far and plug it in and get the first part A wrong. And it's because 0.63, write it down there, okay? If we look at a diffraction grating, what's happening, here's our viewing screen, right? And we have a central maximum. And what is y? Well, y is out to the first m, the first bright spot. That distance right there, that is y. It's not what they asked for, though. They said, what's the distance between the first two M1 fringes? So the other M1 fringe is down here, right? So we have another. So the distance between those is going to be 2 times y. And so when we take 0.63 times 2, we get 1.26. So 1.26 rounded to 1.3 meters. That is the answer for part A, or what is the distance between the two fringes, that there. So now for part B, we need to figure out how many bright fringes can be seen on the screen. Let's come down here, give us some space. So this concept took me a long time to really wrap my head around, and maybe it's not the easiest way to think of it, but what I like to think of is if we zoom in on just a single slit in our diffraction grating, right? The light is coming through and then it gets diffracted. And if it passed through at a straight line, continues on, but it's diffracting off to some angle here, and this is theta. So if we continue on, we could have a bunch of different, let's say this is M1 and this is M2 and so on. Well, what's the maximum possible angle you could get? That's 90 degrees, right? Now, to get the maximum possible one, that's the angle we're going to use. So when we have the equation m is equal to d times the sine of theta over lambda, and this is just rewriting the sine of theta equation. So for sine of theta, to get the maximum possible m, we're going to use sine of 90. If we plug that in, we have m max is going to be 1 times 10 to the negative 3 meters over 600, we said, is our d for this diffraction grating. Multiply that by sine of 90. Now sine of 90 is 1, so we really don't need to put it in there. And then we'll divide that by lambda, which we said was 500 times 10 to the negative 9 meters. Okay, so now when we plug this in, one note that we need to do is we have to make sure that our calculator is in degree mode for this, since we're using sine of 90. If it's in radian mode, sine of 90 will not come out to 1. And so when we plug this in, we're going to get 1 times 10 to the negative 3 meters divided by 600 times by sine of 90. And then when we divide that by 500 times 10 to the negative 9, that gives us 3.33. Now, it has to be the least whole integer. The 0.333, etc., that doesn't count as a fringe, right? Because the fringes are at 1, 2, 3, 4, etc. So for this one, we're going to have 3 fringes. And then they want to know in the question, they say how many bright fringes can be seen on the screen. So it's not going to be 3, because if we draw our pattern, here's the central max, and then to each side, we're going to have 3 more fringes. So we'll have 1, 2, 3. But then over here, we'll also have 1, 2, 3 on our viewing screen. So really, we will have 7 total bright fringes.